Our plan for today. Plan for today.
Yep.
Gonna finish the in-class example from 8-1. Gonna do 8-2. 8-2 in-class example. Talk a little bit more IA stuff, due dates and whatnot, and that'll be that today. Everybody cool?
Bless you.
Bless you. All right. Bless you. Example. There are 105 people in the same grade as each other. The teacher finds out some students are in the same math class, science class, and English class. She finds that 4 students are in all 3 classes together. 12 total students are in the math and science class together. 5 in the science and English together. 9 in math and English together. 40 in math. 26 in science. 50 in English. When you hear the descriptors, there's an extra word put in here that's real important. What word is in each of these descriptors that's pretty important? Total, yeah. So first question is asked to build the Venn diagram. Okay. Who can help me fill in the circles? Brooklyn, go for it.
Going with all 3 would be 4, like in the middle of all of them. Draw them apart. And then 12 would be math and science.
Okay.
And then 5 math and English.
Okay.
And then, oh, sorry, the 5 was for science.
Okay.
And then, wait, so then wouldn't it be, would you do 40 minus 12 minus 4 minus 9 to get the ones that are like just in math, like not the other, no, it's total, that'd be 40, the math, right?
You're saying here?
Yeah.
I asked you. You can't ask me back.
No, I think, no, wrong. Wait. 40 minus 12 minus 4 minus 9. What is that? 30. Wait.
So you want this to be 28?
Yeah, 28 there. And then 26 minus 5 in science is science. Yeah. And then and 32 is the one thing. That I could be wrong, but is that right?
No. So like, Maggie?
40 would be at the bottom circle. Like where 32 was.
Can't do it yet. We need to fill in the other overlaps before we're able to fill in the nons.
Wait. Next to the 4.
What's up?
To the right of the 4 is 1.
So math and science only,
And then 5.
or science and English only, excuse me. And then what?
5 for the other little circle.
Math and English only.
And then the top left is 23.
We gotta do this part first.
Oh, that's 8. And then 23 for the top left.
So 9, 17, and 23 makes 40.
And then 13 for the
8, 4, 1 is 13, and 13 more makes 26.
and then 30, 40 for the bottom.
5, 4, 1 is 10, and 40 more makes 50. And then how about, are there any leftovers? 11, that's right. Let's count. 45, 9, 50, 63, 71, 94, and 11 more makes 105. Okay. So keep in mind here the difference between this problem and the previous one. With total versus just, right? Just, we could just fill the numbers in the right spots. Total, we have to do some subtractions all the way, right? So we did A, that's the Venn diagram. How many students are in none of the classes? Right, you just read off the picture. Who can tell me what n of m complement intersect E is? Katie.
It's 41. You just count everything in English that isn't shared with math, and then also the science and English. So 40 plus 1.
So you're looking at English and you're taking out math, right?
Yeah.
That's kind of the easier way to think about it, right? If it's an intersection. Okay. P of M union S intersect E complement. Who wants to do that one? What's the P out front mean? Probability. So what's the answer going to look like? Ugh. Let's write it as a fraction. What's the denominator of that fraction got to be? 105. Why the 105? It's how many total students we had. All right, so let's figure out how many are in M union S intersect E complement. What's E complement? Everything that's not E, right? What's M union S? Everything in M or S, right? So we're looking at everything that's in M or S, but not still in E. Does that make sense? Oops. Goodness gracious, Mr. Bulik. Oh, come on now. Yes, go ahead.
Just an introduction.
Sorry. That. In M or S, but not. It's 31, 41, 44. That look good to you guys? How about P of S complement intersect M complement union E? The P out front means? So my answer is going to be out of 105. Okay. So my suggestion when I look at this, I'm going to use De Morgan's law And I'm going to think about that really as S union M complement. So what are the things that are not in the intersection of S and M, but also include E? Everybody okay with that? Not in S or M, and also include E. Oops, sorry. And those guys. So you have all of E, and then also the stuff not in S. So 40, 45, 49, 50, 61. Okay? It's all right. Let's get probabilitying. All right, basic rules of probability. Some of these things we touched on last time. Probability of any event is a number between 0 and 1, or a percentage between 0 and 100, or a proper fraction, or say positive proper fraction. Actually, a non-negative proper fraction. 0 is okay. What happens if you give me any other kind of answer for a probability? No credit, right? You give me a crazy answer, no credit available. I'd rather you write down and tell me, like, Mr. Kulik, I don't think this is right, but the answer I got is a crazy answer, so I don't know what to write here, but here's my work. I don't know what went wrong. That'd be okay. I mean, better than, like, telling me the probability is 1.5. That's bonkers. All possible outcomes together must have a probabilities whose sum is exactly 1. So if I add up everything in the sample space, all the outcomes, I should get the same number of outcomes as there are elements in the sample space. To calculate a probability, you just look at the number of outcomes corresponding to event A divided by the total number of outcomes in the sample space. Basically, just like a percentage, right? Part over whole is all we're talking about there. And the last one is that the probability that an event does not occur is just 1 minus the probability that the event does occur. We talked about that last time. We called it the complement rule. So this is the rules in the English language. We could also give you these same rules symbolically. So again, probabilities between 0 and 1, that's the first bullet. All the probabilities add up to 1, that's the second bullet. Calculating a probability, that's the third bullet. And the complement rule, that's the fourth bullet. Just a symbolic version of all of these things. All right, when we talk about probabilities, we can sort, one way to sort these probabilities are into 2 categories. There's theoretical and experimental, right? So let's say that I'm flipping a coin. What's the probability of getting heads? What's that? Yep, 1/2. That's in a theoretical probability though, right? What did you assume when you found that probability? You made an assumption there about my coin.
That's
It's fair. that their heads and tails are equally likely, right? Let's say that you didn't trust Mr. Kulik because Mr. Kulik, like, you're a mathematician. I know you're a sneaky jerk. I don't trust you in this coin. I want to calculate the probability myself experimentally. So I'm going to flip this coin 10,000 times and record how many times I get heads and tails. I'm going to use that to make, or to call, or to use that as my probability of heads. Just the number of heads I get out of 10,000. That's an experimental probability. You guys see the difference? So a place where experimental probabilities are preferred over theoretical. Can we think of a situation like that? Games where skill is involved, right? Like if you're a baseball player, your batting average is essentially a experimental probability, right? We're not calculating, the ball is here and the swing, it looks like, like it's a game of skill. Like it's not your swing being equally likely to be anywhere. If you're a baseball player, it should be closer to the ball than just random. Everybody kind of see the difference there? So in situations where like a skill is involved, you're really limited to theoretical probability, or shooting a basketball, or whatever. These are all like places where it makes more sense to talk about an experimental probability than a theoretical one. Does that feel okay? Even a situation that's like even simpler than that, like throwing darts at a dartboard. Do you guys remember in geometry doing like calculating a geometric probability for like getting a bullseye on a dartboard? Where you found the area of the bullseye divided by the whole area. It's kind of a typical geometry question. That's kind of that's a theoretical probability, but it's kind of a dumb one. Because if you're an actual dart player, is your dart equally likely to land anywhere on the dartboard? No, right? It should land close to where you're aiming, right? If you're aiming for a bullseye, the odds of you missing, like hitting outside of the circle even on the dartboard should be pretty low. You should hit the dartboard. You know what I'm saying? So in a real world setting, experimental probability is kind of where you end up living a lot of the time. In a classroom, though, we kind of are stuck on theoretical probabilities, or situations where like the theoretical probability and experimental probability should be the same, i.e. like flipping a fair coin or rolling a fair die or something. All right, example. A baseball player has a batting average of 250, meaning he has safely hit a ball and reached base 1 out of every 4 times he stepped to the plate. In a particular game, he has gone to the plate 3 times and not yet reached base. Your friend argues that the baseball player absolutely safely hit the ball and reached base at his next at bat. Give 2 reasons your friend is wrong. Anybody got a answer here for us? I hate this stupid thing. One of the 2 reasons. One is from last time. Probabilities are true when? Like in the long run, right? How is this person using the probability though? right? In the short run, right? That's the myth of short run regularity. Now, anybody that's played baseball before knows that like there's stretches where you're like a 500 hitter, and there's stretches where you're like a 100 hitter, and at the end of the season you end up being a 250 hitter, but very rarely are you just like 250 hitter for a long stretch, right? There's lots of little ups and downs, and you get hot and you get cold, and that's the way it looks, right, during a baseball season. So the first one is your myth of the short run regularity. The second reason they're wrong is they're conflating an experimental probability and they're using it as a theoretical probability, right? And that's the other issue. All right. Next up is mutually exclusive events. We talked about this last time also. Remember that the term mutually exclusive we can use interchangeably with the term disjoint, or we could use interchangeably with the phrase, the intersection is empty. All three of those mean the same thing. Okay, so mutually exclusive means that there is nothing in common between the two events, i.e. there's no overlap in your Venn diagram, i.e. the intersection is empty. All of them are kind of saying the same thing. So let's give, who can give me an example of mutually exclusive events? How about if you're flipping a coin?
You'll never get heads and tails of the same one.
Yeah, heads and tails are mutually exclusive events. You flip a single coin, you can't ever get both heads and tails at the same time. Everybody agree with that? Most of our like simple probability games like rolling a dice or flipping a coin, at least in with a single coin or a single dice, are mutually exclusive, right? Now if I'm rolling two dice and the event is rolling a 7, is that mutually exclusive? No, right? There's a bunch of different ways to roll a 7. All right. So if we want to talk about calculating the probability for mutually exclusive events, here's the good news. The probability of A or B, or the probability of A union B, as long as there's no intersection of the two, is just the probability of A plus the probability of B. You can just handle them separately. It's very nice and neat. So the probability of rolling a 3 or a 4, if you're just rolling one dice, is just going to be the probability of rolling a 3, 1 in 6, plus the probability of rolling a 4, 1 in 6. You add them together, that's 2 in 6, or 1/3. Let's look at an example here to illustrate this. When people create codes for their cell phones, the first digits follow the probability model shown in the table below. Just as a side, which number do you notice is the most common first digit for their cell phone passcode? It's the number 1, right? Why do you think that is? If we were going to psychoanalyze people, why do you think 1 is the most common first digit for a cell phone passcode? Isn't ever
passcode.
Passcode.
Well,
It's like an easy
1, 2, 3, 4, probably.
to remember.
Most common
The
passcode.
first number of the thing.
Okay. Maybe I can think of a much better reason though, because those are pretty weak passwords. 1, 2, 3, 4, just 1, 1, 1, 1. What are the most common things that people use as passwords or passcodes? Birthdays, right?
19.
What year are the majority of cell phone owners born? Starts with a 19, doesn't it? That would be my guess, is that you have a lot of people using their birth year or a birth year of someone else as their passcode. The majority of birthdays are in the 19s as opposed to the 2000s. That would be my guess. I don't know. That's just me psychoanalyzing the data here. But that tracks to me. I'm not surprised that 1 is the most common digit. All right. Find the probability that of the event that the first digit is 1. Who can tell me that?
Would it just be 0.3?
It would be just 0.3. You just read it off the table. How else could you write that answer other than 0.3? 30%. Great. How else could you write it? 3 out of 10, or 30 out of 100, or 300 out of 1,000. You know, like those are all fine ways. All of those are correct. You could use them interchangeably. There's no preference given. I think you're crazy not to just use the decimal rule that was given to you. Okay. How about the probability the first digit is more than 5? More than 5. What outcomes are contained in more than 5? Guys.
6, 7, 8, 9.
6, 7, 8, 9. Everybody agree? Are those outcomes mutually exclusive? Can the first digit be both 6 and 7? No. Are they mutually exclusive?
Yeah.
Yes. Right? You can't be both 6 and 7, or 7 and 8, or 8 and 9, or 9 and 6, or whatever, right? The first digit can only be one thing. It can't be two different things. So how do we calculate the probability of the event that contains the outcomes 6, 7, 8, and 9? Since they're mutually exclusive, we can just add up the individual probabilities for 6, 7, 8, and 9. And that gives us 0.221. Very easy, right? No big deal. All right, what about that the first digit is odd? What event or what outcomes are contained in the event the first digit is odd? 1, 3, 5, 7, 9. I forgot the 7.
Yeah.
Oh my gosh. Are those outcomes mutually exclusive? Yeah. Right? So just add them together once again. And we get 0.603. So far, so good? Okay, how about the probability the first digit is 1 or greater than 5? Notice that this is a compound event. This is a union. What word in this event tells you that it's a union of two events? Or is correct. So how many outcomes are in the event? The first digit is 1. Just 1, right? How many outcomes are in the event? The first digit is greater than 5. 4, 6, 7, 8, 9, right? Are there any outcomes in common between those two events? 1, 6, 7, 8, 9. No overlap, right? We'd say those events then are mutually exclusive or disjoint. So to calculate the probability, we can just add the probability of 1 and the probability that the greater than 5, which we had calculated previously. We just add them up together. 0.521. Everybody's okay there? Continuing on, some more examples. How about the probability that the first digit is not 1? What kind of an event is not 1?
Complement.
It's a complement. What's the easiest way to calculate the probability of a complement?
Subtract probability of 1.
Yeah, using the complement rule. So to calculate the probability of not 1, the easiest way is to do 1 minus the probability of 1. How many outcomes are in the probability 1? Just 1. How many outcomes are in the probability not 1? 9. Which one would you rather deal with? 1, right? That's way easier. So using the complement rule, we get 0.7. Alternatively, you could add up all the other probabilities. In this case, there's only 9 of them. It's not that bad. But if there was, say, like 1,000 or 10,000 or infinitely many, oh dear, the complement rule is pretty powerful. Mr. Kulik, are we going to really deal with situations where there's infinitely many outcomes? Yup! Oh no! It'll be okay. Example. Find the probability the first digit is an odd number or a number larger than 5. What kind of an event do we have here? A union. How did you know it was a union?
Because it was or.
The word or. So how many outcomes are in the event an odd number? 5. Those events or those outcomes are 1, 3, 5, 7, 9. How many outcomes are in the event a number is larger than 5? 4. Those outcomes are
6, 7, 8, 9.
6, 7, 8, 9. Are those two events mutually exclusive?
No.
No! Ooh, gotta be careful then, right? Why are they not mutually exclusive?
Because there's odd numbers in the larger than 5.
Yeah, they both include the number 7 and 9, specifically, right? So when calculating this probability, we need to be really careful because we cannot just add up our two previous answers because they are not mutually exclusive. Instead, you should do this individually. Odd or larger than 5 is the numbers 1, 3, 5, 7, 6, 7. 1, 3, 5, 6, 7, 8, 9. We'll add them up individually. See, look at the overlap, right, between 7 and 9. And so we get 0.721. Notice that is decidedly different than if we added the probability that the number is greater than 5 and added the probability that the first digit is odd. You get a very different answer, right? Almost 10% difference. Why are we getting the wrong answer there? Because I'm double counting the probability of 7 and the probability of 9. Right? Those probabilities are included both in the event B and in the event C. So if we have non-mutually exclusive events, so overlapping events, you want to calculate the probability of a union. You can do the probability of A plus the probability of B, but then you need to subtract the probability of A and B. So you have to subtract off the intersection because you counted that intersection twice. That'll be a formula later on. There we did that. Okay. That's all she wrote for the notes. Let's do the in-class examples now for this. All right.
That's a credit.
Random inattentive students, I'm now going to call on you when you're not paying attention. Ooh, scary. Or I might just take some volunteers. So it says below is the probability model for students who took the 2013 AP Stats exam. Part A says prove that the model is a legitimate probability model. Check. What do we have to do to show that that is a legitimate probability model?
You gotta, use the table
Okay,
to show it.
how so? You're right, the information we need is in that table.
We need to find out like the common score maybe.
The most common score?
Yeah.
Nope. Jackson, you want to help him out?
Yeah, the probability is to add up to 1.
The probability has to add up to 1 for all the different outcomes. So we just need to show that like P of 1 plus P of 2 plus P of 3 plus P of 4 plus P of 5 is equal to 1. So 0.235 plus 0.188 plus 0.249 plus 0.202 plus 0.126. And they do add up. You trust me? I wouldn't, but I'm a math teacher. I'm a sneaky jerk by profession. Kirsch.
For this one.
Yeah, go ahead.
Pretty sure you're supposed to add probability score of number 1 and number 2.
So at most 2 is
1
less than or equal to, right? And because these are mutually exclusive, we just add them together. Everybody feel good? I don't have to actually crunch the numbers for this, do we? Like the setup's enough, I think.
Yeah.
The probability that a chosen student score is at least 3. What's at least mean?
It means
Greater than or equal to, yeah. So to do that, we would need to do the probability of 3 plus 4 plus 5 plus 6. Everybody feel okay with what we did there? There are 30 students in a stat class. After taking a poll, the teacher discovers 20 students play an instrument, 18 take art, and 12 do both. Draw a Venn diagram to represent the situation. Who can help me fill in the Venn diagram? Go ahead, Ethan.
You have 20 students in instrument 1, 18 students in art, and 12 in middle.
Okay, here's my problem though, Ethan. If I add those up, I get 50 students.
Is it so?
Let's start there. How many people have been placed in the I circle?
12.
12. How many should be in the I circle at total? 20. How many more do we need to add? Okay. If I add those up, what do I get? Okay, where do the other 4 go? Katie says outside. Is everybody okay?
Yeah.
All right. How many students take art but do not play an instrument? So that means the number in the set A intersect I, or not I. That's that section. Is everybody okay there? Yes. Sure. Now it's going to be important as a fair warning. You're going to have to be able to read those things and turn them into probability statements in addition to just finding the answer. You know, like A intersect I complement and stuff. You should be able to do that. That'll be a helpful skill in this chapter and future chapters, just as a fair warning. What is the relationship between educational achievement and home ownership? Burning question in all of our minds. A random sample of 500 U.S. adults was selected. Each member of the sample was identified as a high school graduate or not, and a homeowner or not. The two-way table displays the data. Use symbols to define all possible events for the data above, using high school graduates G and homeowners H. So homeowners H, high school graduate is G. What's not? How would I show not homeowner? H complement. And how would I show not a high school graduate? G complement. Everybody happy with what we did there? Okay. Suppose you choose a sample. Suppose you choose a member of this sample at random and find the probability that the member you choose is a high school graduate. Since it's a probability, how are we going to write this probability? Probably a fraction, right? What's this fraction going to be out of? 500. How many high school graduates do we have? 310. Everybody's good? Do you need to worry about reducing fractions for like the test or whatever? No. Don't bother. No.
That's nice, thank you.
Yeah, it makes no never mind. We don't have to worry about reducing fractions. Just write the fraction. Proper, improper, well, never improper, right? But like reduce, not reduce, who cares? Nobody cares. Find the probability that you have a high school graduate and are a homeowner.
221 out of 500.
221 out of 500. 221 is an insane answer. I'm glad you added the out of 500 though. Okay? High school graduate or owns a home.
Plus 340 out of 3.
No, that's an insane answer again, right? What happened there?
Because there's people that own a home and are high school graduates, so you have to subtract the 221.
Yeah, you would have double counted the 221. Alternatively, you can just do and add the 3. Is everybody okay with what we did there? I'm just going to write it that way. It's probably clearest for everybody to go back and look at it if I write it that way. You know what I'm saying?
Yeah.
But you could have done what Maren suggested also, and like take the 2 and then subtract. I think most of us are probably going to do what I did upon practice because it's just a little bit quicker. Not that you said it was wrong. Perfectly fine. Totally reasonable. Using the two-way table above, construct the Venn diagram, which contains graduates and homeowners. Okay, where does the 221 go?
In the middle.
In the intersection. Where does the 89 go?
Show us some high school graduate part.
Okay. And H not G is here. Where does the 119 go?
Wait, isn't it backwards?
Did I put it in the wrong spot?
So 89, but
89 is graduate. Sorry. Okay. Where does the 119 go?
and the other half or part.
Okay, and the H not G spot, H only. And then where does the 71 go?
Outside.
Outside. That's a skill you need to have. To be able to take a Venn diagram, build a two-way table, or take a two-way table and build a Venn diagram. I think we talked about that last time a little bit also, right? Again, once you've done it, it's not difficult, but like doing it for the first time, it's like the symbols can get tricky, right? Okay, that's it for today content-wise. I just want to run over some deadlines that we have. Friday, what's due Friday? Introduction. How do you turn that in? Email it to me. As a Word document. Google Doc is okay though, for an introduction, but like, don't write your paper in a Google Doc, just use Google Doc, right? Because you're gonna have to, even if you write your introduction as a Google Doc, you're gonna have to transfer it into a Word doc to do your equation editing anyways. That's Friday. Your Excel sheet with all your calculations in it, when does that due? Monday we come back from break. I'm not positive on the date.
It's this first.
The first, great, easy. What do you need to do that? I can't remember how to do any of the stuff on there. What do I do? Oh yeah, there's a video spelling out how to do that, right? Okay, if you have questions on it, it's in one around the minor name under the links, and it'll be called something like I8 data Excel sheet or something. You see it? Yeah. Okay, and then when is the full hog paper due?
The following.
The following Monday. So that would be the 8th then if the data was on the 1st. Everybody's okay with that? We're good on the dates. I think I have those into minor name already. How long is it going to take to actually like sit down and type out and write your IA?
10 hours.
Like 10 hours, right? Don't try to do it in one sitting. That sucks. It's hard. You're going to make typos and mistakes, and it's not going to read well, and spread it out. Okay? Give yourself at least a day to sit on it before you go back and read it and try to edit. Can you start now? Yes, right? We should be writing introduction right now. You can write your data collection section right now. You can write mathematical processes right now. You can type in the equations that you're going to use into Word right now. You can make a glossary of symbols that you'll have to add, be able to like cut and paste from every time you want to talk about R or chi-squared, or all those things have like a mathematical symbol. I would just have a page at the end where I type in those symbols that I'm going to use commonly, so I can just cut and paste them rather than having to go into equation editor every time I want to, talk about the Pearson product moment correlation coefficient. Everybody cool? So don't try to leave it all at once. I know it's tempting to say, oh, that's 3 weeks away. Try to get some hours in before it's time to like really sit down and write the bulk of it. Obviously, you can't write your results section yet. Not until you finish your calculations. You can't write your conclusion until you've done the results section, right? But up until that point, you can really write a lot of your IA now. I would suggest like doing that and kind of getting started. You have some free hours here over the break. Try to find a couple of hours and try to bang out a section or two. Okay? Give yourself a chance to reread and go, God, this is tremendously boring and like not very detailed, not very, pretty vague, and go back and be like, I can do better than this. The first pass that you're gonna write is probably gonna be vague and kind of crappy. If you turn that in, I will be generous, but only to a point. Really, you want to make sure that you're being specific, being detailed, and be introspective. Like why you're doing what you're doing. What is this result telling you? Why? How does that inform the next decision that you would make? Like how one calculation leads into the next calculation. You know what I'm saying?
In your introduction, we don't have to reference the equations, right? Like, it's just why we're doing what we're doing.
You can talk about your plan, but I wouldn't go past a general outline of like, I plan to, I'm gonna collect this data, and then I'm gonna look at the scatter plot, and then do like a numerical analysis to look for an association using a chi-squared test, and then look at, if, depending on the result of that, maybe look for a linear correlation by doing the Pearson product moment correlation, and if that comes out good, build a trend line so I can make predictions about future behavior, like give a general outline of like what your plan is gonna be. Now, if the results that you're getting indicate maybe you shouldn't do that, that's okay. Or that your results show nothing, right? Like if you find that the two variables are independent and you do a correlation, you'd expect to find weak correlation if there's no dependent relationship, and that's fine. You can find nothing that the two things that you're studying appear to have no relationship at all. That is okay. You do not get deducted for that.
Okay.
Right? Like, you can show absolutely nothing works. That's okay. The point is you are able to communicate what you're doing and why, and how you decided what to do next, how you know what the thing means, how you justify that, hey, I should do this and this is going to be valid because, my chi-squared test passed the randomness condition and the large counts condition. What are those and how do I know it passed? Like that's the kind of stuff that you can talk about regardless of you get a result that means anything or not.
Okay.
Does that make sense? That is the final. So there is no in-class final. So you guys will be done, with that. We're gonna take a chapter 8 test before the end of the year, I think, or for the end of the semester. That'll be the last thing you'll be responsible for.
So the completed IA is due December
8, I think.
And that
What
would be
would and spot something and we really
That's insane. Oh my god.
I don't believe that.
That's
Actually,
Are they all just
Histories are final though, so I think that might be
Well, mine is,
Understand how much time
I
we put our heads on these things with
dibs on the
CCL.
week after Thanksgiving.
Yeah.
And I think everyone else is just kind of floating on the side because there's so little time between Thanksgiving break and Christmas break.
Yeah.
But this is like the time on the IA,
We got hours.
this is
Hours
the,
and
that is the
hours.
time
Like-
for the
Tuesday's pretty
IA.
much done.
I wish we had
that.
history.
I'll get you some more.
I wish we had last year.
I know. That's what Alvin did.
You're still right.
No, barely.
If they don't have a bio, that'd be so bad.
And that's the one thing I'm grateful
Especially
about.
acknowledge that.
He's not.
But I did